So we've talked about Newton's second law as an equation. We talked about what that equation means, what it's trying to tell us. Now let's come back and talk about the specifics of how we're going to work all these Newton's second law problems. So again, this is a situation where we're going to work tons of Newton's second law problems, so we really want to understand what the process is. That way, instead of feeling like this is thousands of problems, really what we recognize is we're doing the same thing over and over and over again. So what's that process? Well, we're going to start the same way we always do. We're going to draw a sketch. And we're going to take that sketch and we're going to use it to draw the vector diagram. In this case, that vector diagram will be the free body diagram. We will start with problems where we're interested in a single free body diagram because we're interested in one object, the forces acting on one object. We'll end up working with problems where we have multiple objects, and in those cases we'll draw multiple free body diagrams. But we'll always start by putting together our sketch, and make sure we can turn the words into the right picture, and then using that picture to come up with the free body diagram that we need. Then we're going to pick a coordinate system. And again, one of the things that we'll emphasize is knowing the direction of the acceleration helps. So if what we do is use the direction of the acceleration as one of our coordinate directions, that's going to really simplify the math in the problem. So we'll use what we know about objects speeding up or slowing down to figure out what's going on with the acceleration, and then use that to help us pick a coordinate system. Then we'll break both the force and the acceleration vectors up into components. As a general rule, students are really good with this one. They're going to have a very clean picture in the free body diagram. We're usually pretty good at this point in the course in breaking those force vectors up into their components. It's the acceleration vector, oddly enough, that we often struggle with, whether we just forget to do it, whether we just get the wrong components. So we got to break both the force vectors and the acceleration vectors up into their components, and we got to remember to do both. Then we're going to set up Newton's second law equations, and again, because Newton's second law is a vector problem, we have one equation per dimension. If we just have stuff, if all of our forces lie along a single line, then we just have a one-dimensional problem. If we've got stuff pointing horizontally and vertically, then we've got a two-dimensional problem. You will certainly run into problems, not likely in this class, but you could run into problems where you talk about stuff pointing in all three dimensions, and then you'd have three equations. So we're going to set up the correct number of equations we need depending on how many dimensions we've got in our problem. Then we're going to determine the magnitudes of those vectors. So the idea is that some of the force vectors we will have an expression that we can use to calculate the magnitude. Some of them we won't. And we've got to make sure that we use those correctly. A lot of times students will be perfectly fine getting to here, and they'll actually make a significant number of mistakes in terms of dealing with the magnitudes of the vectors that they know. They'll try and create equations for magnitudes of vectors that don't apply. So we want to make sure that we plug in the right magnitudes or the right equations to calculate the magnitudes for our vectors. And then the last thing we're left with is solve for the unknowns. And again, if we've got a one-dimensional problem, then this is one unknown. If we've got a two-dimensional problem, then I'm going to have two equations, one for the x, one for the y, and I'll have two unknowns. So basically, this is you can think of this as the flow chart for how we're going to work through a Newton's second law problem. And in fact, part of what we'll do in class is emphasize what are the important questions that we basically need to ask at each step to make sure that we're doing that step correctly. So let's see a very, very simple example. So this is just going to be a one-dimensional problem, very simple example. But it'll give us sort of again, kind of an idea about the process here. So what we're told is we've got two horizontal forces that act on a 2-kilogram box as it speeds up while sliding to the right across a frictionless surface. So force 1, which is drawn in here, has a magnitude of 6 newtons and points to the right. Force 2, right here, has a magnitude of 2 newtons and points to the left. We want to know what's the magnitude and direction of the acceleration of the box. So you notice a couple things here. One is, here's my sketch. In this case, it's effectively already provided. That's fine. We're going to end up we'll draw the free body diagram down here, right? You can see where I've drawn the dot to represent the center of mass for my box. So I'm going to draw the free body diagram down here, but I know that only force vectors should go in my free body diagram. There are some other relevant vectors within the problem, one of which is the velocity vector, and I've drawn that in my sketch. So one of the things that I'm going to strongly encourage you guys to do is draw out the velocity and acceleration vectors, but just to do that within your sketch rather than doing it within your free body diagram, so you don't end up confusing yourself because you've got these extra vectors that are sitting in your free body diagram. Now we know the velocity points to the right, but we also know that our object is speeding up. So speeding up tells us that the velocity and acceleration have to point in the same direction. So here's a situation where, sure enough, velocity, acceleration, both point to the right. And again, this is going to be information that I use. So I'm going to use my sketch to draw in the velocity and acceleration vectors and not put those into my free body diagram. Okay, so now I can draw my free body diagram. Step 2. So the first question I want to think about, right, I'm going to run through the series of questions that we've been working on in class, and the first question I need to think about is, does my box have mass? Sure enough, it has a mass of 2 kilograms, so I need to draw in the weight. Is my box in contact with the surface? Yes, it's in contact with a horizontal surface that sits beneath it, therefore there's going to be a normal that points up, so there's the normal. Do I need friction? Well, in this case, I'm told it's a frictionless surface, so no, I don't need friction here. I just have the normal in terms of the contact between my box and the surface. Next question, do I have a rope or a string or a chain or anything that acts like that? No, so I don't need a tension force. Next question, do I have any applied forces? And yes, here I obviously have 2. I have F1 that points to the right and F2 that points to the left. I know that F1 is 6 newtons, I know that F2 is 2 newtons, so again F1 is clearly larger than F2. Alright, so that's taking care of all the forces that act on the box. And so now, step 3, pick my coordinate system. Well, again, we said we want to pay attention to the acceleration. And so I know that the acceleration points to the right. So what I'm going to do is I'm going to choose a coordinate system that says the acceleration points in the positive x direction. So what we're almost always going to do is basically say the acceleration points in one of our positive directions, and in this case I'll just happen to choose it to point in the positive x direction. So the coordinate system I want to use for my free body diagram is the same one. So you notice that I'm picking the same coordinate system. And here's now the set of vectors that I'm going to need to break up into their components. Here are all the force vectors I need to break up into their components. Here's the acceleration vector that I need to break up into its component. So I've picked my coordinate system, again, taking advantage of what I know about the acceleration. All right, fine. Next detail is break these vectors up into components. And so I'm going to set up my table. And again, I'm going to have the set of forces, and then also MA, where I need to think about the x component of each force, the y component of each force, and I need to think about m times the x component of the acceleration and mass times the y component of the acceleration. So as I go through this, well, what I notice is the normal force points straight up, so it's going to have an x component of 0. The y component is just going to be the magnitude of the normal force. My applied force F1 points to the right, so it's got a 0 for its y component. All of its magnitude is in the x, and it's in the positive direction. The weight, straight down, so its x component is going to be 0. The down means it's going to be negative, and this is just the magnitude of the weight. F2 points to the left, so its y component will be 0, its x component will be negative, and this is all the magnitude. And now what I got to do is say, okay, what's the x component of the acceleration? Well, it's all of the acceleration. So in the same way that we said, hey, for F1, it points along the positive x-axis, the acceleration also points along the positive x-axis. So this is just positive, the magnitude of the acceleration, and that gets multiplied by mass. So the x component of the acceleration here is just positive a, and then I multiply it by mass, so it's just ma. The y component, well again, the acceleration lies entirely along the x-axis, so the y component is 0. So the y component of the acceleration is 0, multiplied by mass, you still get 0. So here are the 4 force vectors and the acceleration vector broken up into their components. So what do I do with this? Well, the next step is I want to use this to set up my two equations. So I'm going to set up one for what's going on in x. And so it says that the sum of the forces in the x direction, this plus this plus this plus this, equals mass times the acceleration. My second equation is basically the same thing, just in y. So the sum of the forces in y, so the normal plus 0 minus the weight plus 0, equals mass times the y component of the acceleration. So all that's got to equal 0. So here are the two equations that I set up. In this case, what I'm asked for here is the magnitude and direction of the acceleration of the box. And I look at it and say, well, this doesn't include the acceleration. This equation does. And since I know the value of these other two forces and the mass of my box, it's easy enough to just take this equation and solve for a. So all I'm going to do is basically just, plug in 6 minus 2 equals 2 times a. So I get 4 equals 2a. A is just 2 meters per second squared. So this is easy enough, once I've got this set up, to simply solve for what the magnitude of the acceleration is. And again, in terms of its direction, well, I know that's in the positive x direction in my choice of coordinate system, which pointed to the right. So the acceleration here is a vector 2 meters per second squared in magnitude that points to the right. Now, we said there's two equations and there's two unknowns if I've got two equations, and in this case the other unknown happens to be the normal. So if there was a part B to this problem, let's say, that said what's the normal acting on the box, well, now I could use this equation to solve for it. And so sure enough, that's simple enough as well. And again, what I do is I get, the normal equals the weight, and here's again where I'm going to plug in for the magnitude of this force. So I knew values to plug in for the magnitude of these two forces, and I know an equation to plug in for the magnitude of this one. It's just mass times gravitational acceleration. So I can solve for the normal. It's just 2 times 9.8, which is 19.6 newtons. So this is the basic structure that we're going to do sort of over and over again as we're working through these Newton's second law problems. So I want you guys to have a little sense of familiarity with it. Again, you can sort of, bring to class that flow chart, and then again, we'll sort of fill in, kind of leave yourself some space in there, and we'll fill in, take some notes on what are the important questions that we should be asking as we go through each step. And then largely, you're just going to get a ton of practice because you're going to get to work a ton of Newton's second law problems over the next couple of weeks.